Hello, I'm Supun Gamla and welcome to the video of my research and development project named NeuroFall, conducted under the supervision of Dr. Chaturanga Hettiaraj. First, to introduce my project, let's break down the topic. My project is a hardware system built on an FPGA which uses an event camera to capture visual events, which will be processed by a spiking neural network to raise an alert when a human fall is detected. A spiking neural network is a neuromorphic artificial neural network architecture which mimics the functioning of biological neurons. The objectives of this project are to create an event dataset for fall detection, train, simulate, and evaluate a spiking neural network, then implement the spiking neural network on FPGA and evaluate the performance, power efficiency metrics of the system. The research methodology is shown here. It consists of four major steps: dataset preparation, model development, FPGA implementation, and system evaluation. Under dataset preparation, a dataset was selected and its RGB video was converted to event-based format using the V2E toolkit. And in addition to the proposal, this V2CE toolkit was also used as an extra work. Also, the dataset was validated and model development was started. The original proposal only included a feed-forward SNN, but I was able to complete both recurrent and a novel uniform architecture, as we shall see next, during model development. The FPGA implementation included a VHDL design for the feed-forward SNN, as well as the recurrent SNN, which was optimized and simulated with Xilinx Vivado. Unfortunately, the deployment on FPGA could not be completed for the larger model because of the unavailability of sufficient hardware. Therefore, a smaller model was deployed for demonstration. The system was evaluated and performance as well as power consumption was compared. Here we shall see the dataset preparation process. In a traditional frame-based sensor, the whole sensor array is triggered at a predefined frame rate, regardless of the actual seed. This leads to acquisition of large volumes of raw, undersampled data continuously. In a dynamic vision sensor, as shown here, each pixel activates itself depending on the intensity change it detects. This acquires only a small volume of essential motion information asynchronously. Here, two methods called V2E and V2CE for conversion of video datasets to events is shown. The source dataset I used was the UB fall detection dataset, which was converted to DVS events at a lower resolution and a higher temporal resolution using these tools. As you can see, these tools follow two different methods. While V2E uses a mathematical model, while V2CE uses a pre-trained neural network. And when comparing the results, we cannot identify a clear advantage of either tool over the other. So the V2E dataset was used in the following experiments. The feed-forward spiking neural network architecture originally proposed is shown here. The neuron model is the leaky integrate and fire neuron, which resets by a subtraction mechanism. Since neurons, the leaky integrate and neuron model is not differentiable, we use the surrogate gradient method using a fast sigmoid function to handle the non-differentiability. With the following hyperparameter search, the best binary and multi-class models were identified for this architecture. Shown here is the recurrent architecture that we developed. It also uses the Leaky integrated fire neuron with the subtraction reset mechanism, but the gradient function used was the ATAN function. This is the novel uniform architecture that we introduced. While there have been Spire uniform architecture in the artificial neural network space, this was the first spiking uniform architecture developed in the spiking neural network domain. It uses leak integrate and fire neurons in the hidden layers, while the last layer contains leaky integrate neurons. It also uses a reset by subtraction mechanism as well as a surrogate gradient function of ATAN. Spiking multi-head self-attention was implemented along with learnable position embeddings and a convolutional layer for processing images. Shown here is the training process we follow. ClearML was used as the pipeline for running experiments and easily deploying models. The models were trained using a supervised learning approach with batched input and output. Backpropagation through time was conducted with an Adam optimizer, and for the binary classification task, the weighted cross entropy loss function was used, while for the multi-class classification task, an unweighted cross entropy loss function was used. The primary evaluation metric was the F1 score, which combined recall and precision, which are both important for fault detection. The ascendants were evaluated on the UP fault detection dataset, which was converted to events using the V2E tool. Both binary and multi-class classification was conducted. The dataset split first based on the strategy proposed by Espinosa et al. For comparison with existing literature. This used 1 second non-overlapping windows, and the data was split by subjects and trials as shown below. When comparing the results of binary classification, these gray lines indicate ANN models which were trained on the UP4 dataset with the same data split. As we can see, uh, the green color lines, which represent the SNNs trained by us, perform better than the existing SNNs, but it does not pass the state-of-the-art ANN models. The multi-class classification also shows similar results, with SNN performance being better than current SNNs, while not reaching the F1 score of state-of-the-art ANNs. However, the energy consumption shows a different result. When comparing the uniform architecture, which was the state-of-the-art model for fault detection, we can see that the spiking uniformer consumes about 950 times less energy per inference. As we can see, SNNs are clearly more energy efficient than artificial neural networks while retaining acceptable accuracy and an F1 score. The FPGA hardware implementation was done using Vivado and VHDL hardware description language. The architecture of the developed hardware design is shown here. Since this is a recurrent spiking neural network, we can see recurrent connections between the middle layer and the previous hidden layers. The voltage RAM bus width was 8 bits, while the weight ROMs were stored with 4-bit quantization. Even with 4-bit quantization, the BRAM available in the Nexus A7 FPGA is not enough to store the full model. Therefore, this architecture was uh, verified with a smaller network for MNIST classification. This model was quantized as shown here, and we can see that even with quantization, the spiking neural network retains accuracy. So 4-bit quantization was picked as the balance bit as a good balance between model size and accuracy. Shown here is the state machine followed by the spiking neural network hardware implementation. As you can see, each layer takes n clock cycles, with n being the number of neurons in that layer. This slide shows the deliverables of this research project. The event-based fall detection dataset converted using V2E and V2C was released publicly on Zenodo, which already has some downloads. The trained SNN models for feed-forward recurrent and spiking uniformer were made publicly available. The fall detection hardware design made using VHDL was made publicly available, and 3 research papers were submitted to these conferences, shown here. Thank you.